Alright, so here we are with Chapter 3, Section 6, the last section in our chapter, and we're doing financial problems involving interest. Woot! Alright, so formulas that we're going to know, and of course this would be on your formula sheet as well. If you are talking about interest compounded annually, which means that whatever you have sitting in the bank there, the bank multiplies by a percent or a rate, and then it says, oh, here, we're going to give you 2 more cents because you kept your $1,000 in the bank. Basically, the bank wants to have money in it so that it can lend it out. Okay, so it gives you a little bit of a boost every time that you have extra money in there that you don't touch. So, of course, who has extra money lying around? Not me. Alright, so we also have, other than interest compounded annually, which is what my bank does, sometimes, depending on what you're investing in, they might do it a certain amount of times per year, which is super awesome, because what happens is, let's say in the middle of the year, you end up getting interest on your account, okay, and then at the end of the year, you have that interest, and you get to get interest on that new interest. So you're kind of saying, oh, well, I got $100 interest, but now I'm also going to get that $100 plus what I already had at a new interest. So it's helpful, okay? The more times per year that you would end up having your interest taken or compounded, that's going to give you more money. After that, we also have continuously, which is actually the whole point of having our value of E. Because this idea is that it's taking this rate, and it's actually making it so often that you're taking the interest that it ends up being infinitely or continuously. Okay, so it's pretty awesome. The idea, again, is that you are now going to be at this rate where it's going to do it continuously, like the second before to the next second, okay? Which, of course, a percent of a percent is pretty small, but it does help if you have a lot of money, so yay for those people. Alright, so what we're going to do here is we're going to talk about an investment. So let's say you invest $2,000, okay, because who doesn't? After doing some research, you find 4 different options for investing your money. I ended up doing this for my kids for college funds. So the idea is that you look through each of them, and actually what I was looking for more was what amount you needed to start in order to gain this interest. But the idea is that apparently Bank One, if you have this $2,000, will offer an 8.75 annual percent rate. Okay, so if you look back at our formulas, that's going to be this guy here. Okay, then Bank 2 offers an interest rate compounded monthly. Okay, and so that looks back at this equation and says, oh, well, K is going to be 12 when we're talking about months. Alright, then Bank 3 talks about compounded quarterly, so 4 times a year versus 12 times a year. And so that would mean that our K is 4, so we're using that equation. And then the last one has your compounded continuously rate, and so again, that's where you're going to use this equation. So we're going to go ahead and evaluate each of these and figure out where we should invest our money. This next slide after this is actually the same thing. It's just kind of giving you this base for figuring it out. So either way, we've got some room here. So in the first one, in Bank 1, remember that we're using our equation for annually here, so A equals P 1 plus R to the T. And for Bank 1, we have a P, or a starting amount, of 2,000. And then we have an R, or a rate, of 8.75, which we're going to count as its decimal equivalent, so 0.0875. And then our T, which we're not talking about specifically in this problem, and so instead we're going to just put in a T of, well, whatever we want, but we'll do 1, because then we can see what happens after 1 year. Alright, so going ahead and plugging these in, let's see, we have 2,000 instead of a P, 1 plus our rate of 0.0875, and then to the 1. So what does that mean? After 1 year, we're going to end up with $2,175. Super. Alright, so then we're going to do Bank 2. And Bank 2, as all the other ones, are saying that we're going to start with $2,000. Our rate for this bank is 0.087, because we're moving the decimal 2 to the left for a rate from a percent. And then, of course, we're going to do it after 1 year, otherwise we can't compare very nicely. The last thing that's in here is compounded monthly, and that's our K value. So we've got K is 12. And now we can put it into our equation. Our equation is A equals P times 1 plus R over K to the KT. And so, if we plug in each of our pieces here, we're going to have 2,000, as we did in the previous problem. Then 1 plus a fraction, having our numerator as the rate, which is 0.087, and then divide that by 12, and then bring that to the 12 times 1. Alright, so if we evaluate this, inside the parentheses, the fraction goes first, so 0.087 divided by 12, add a 1 to that, bring it to the power of 12, and then multiply by 2,000, doing that order of operations. So that leaves us with $2,181.11 if we round up. So clearly, Bank 2 is going to give us a little bit more money after year 1 than Bank 1. Alright, moving on, let's see what happens with Bank 3. Bank 3 again has a initial value of $2,000. It's going to have a time of 1 year. This one has a rate of 0.089, and then it has a K value of quarterly, so 4. So if we plug it into our formula, again, P, same one as before, 1 plus R over K to the KT. That means that we're going to have 2,000 that we're going to multiply by 1 plus a fraction of R, which was 0.089 in this bank, over 4 to the 4 times 1. And so, as we did before, we'd start with our fraction, 0.089, divide that by 4, add a 1 to it, bring it to the exponent power of 4, and then multiply it by 2,000. And so we're going to get 21.84 and 3 cents. So as we move through here, notice that Bank 3 is now the best one. Alright, then our last one is Bank 4. And so Bank 4 says that if you give us that $2,000 after a year with a rate of 8.5%, which means 0.085, we have interest rate compounded continuously, so we don't have any other values, but that means that our fraction, or our formula, is PERT. P-E to the R-T. And so if we evaluate, we get 2,000, and that's going to be multiplied by E to the R, which in this case is 0.085 times 1. So order of operations says E to the 0.085, and that times 2,000 leaves you with $2,177.43. Now, clearly, the one with the highest rate is most likely going to be the one that works, which is what happened here, because Bank 3 is the one that is the best offer. Okay, but of course you'd think something compounded monthly might change that, right? Something that's going to happen more often or compounded continuously. And so just kind of thinking about how those all worked in there, you did want to kind of take the time to do each of them. So another way of looking at this same problem is actually looking at annual percentage yield, okay? And so if we look at annual percentage yield, this is actually easier for us to compare each one of them, because we're saying, oh, we'll just take this percentage that we can compare to another percentage and have a nice comparison or equal playing field. So, an annual percentage yield, we're talking about getting a rate from that. So it turns out that if we kind of break this up into the ideas from before, Bank 1 doesn't really have to change. So Bank 1's annual percentage yield is just what it's saying it is, so 8.75%. Okay. So then after that we have Bank 2. And so Bank 2, it takes this rate, or this number of times that we're doing, and subtracts by 1. So if we fill this in, we're going to have 1 plus a fraction of our rate, which is 0.087, over our k, which meant it was done monthly, and then bring that to the k, and subtract 1. So if we calculate this APY, we're going to do 0.087 divided by 12 plus 1, all of that brought to the 12th, minus 1. And so we get a decimal of 0.09055, but of course as a percent, that means that we're going to have 9.06%. Okay. Then we have Bank 3. And so Bank 3, again, if we plug it into this formula, is going to be 1 plus our rate, which is 0.089, over quarterly, which is 4, and raise that to the 4th power, and subtract 1. And so if we do that one, we come up with a decimal of 0.09201, which means for percent that we're talking about 9.20%. So again, the largest percent so far, as we saw in the previous evaluation. And then we've got Bank 4, and Bank 4 is taking our compounded continuously, and so basically what compounded continuously does is that it brings all of this 1 plus r over k to the k, it brings that into e. And so really we just need e to the k. Sorry, e to your rate. And so it's going to be e to the 0.085. And so we end up with a decimal of, let's see, e to the 0.085. Sorry, I forgot the formula has a minus 1 at the end. Let's make sure we do that. Alright, so we end up with 0.08871. And so if we move our decimal 2 to the right, we're going to end up with 8.87%, which of course is less than the other 9.2. So again, Bank 3 is the best. Again, now instead of comparing dollar values, but percents that are congruent to each other, or at least comparable to each other. Alright. So this is where we kind of have to use our brains a little bit, because we want to be careful for this because it's a loan. So what happens with a loan is that you want a lower percent rate so that you get less amount, versus the saving, which we had before, where you'd want the higher percent. Okay. So again, higher percent was what we were going for before, but now we're talking about a loan, and so we want the lowest percent. So taking a look at each of these, it's probably best to just compare our APY. So if we look for option 1, we're going to end up using our equation of 1 plus the rate as a decimal over compounded weekly, so that's 52. Daily, the next one is going to be 365, because apparently I just forgot how many days were in a year. And then continuously is going to use that e to the rate minus 1. So, let's see, then we have to subtract a 1. So, if we get that, we end up with 4.65%, because of course it is a decimal of 0.0465, but we want the percent to compare. The next one, option 2, is giving us a 1 plus 0.045, no extra 5s there, divided by 365, but then raised to the 365. Oh, I forgot to write that this one was raised to the 52. All of that is going to subtract a 1 and end up with 4.6%, which came from 0.046 as a decimal. And then the last one, option 3, has your 1 plus your, oh, right, we're doing e. So it has e to the rate, which is going to be 0.046 minus 1, and so we end up with 4.7%, which came from 0.4707. Oh, 0.47. Okay, so if we take a look at this, again, this is a loan, so we want the lower percent. And so the lowest percent is going to be 656, yeah, 4.6. So, lowest. Alright. So, normally they won't have you compare like 3 or 4 different things, but of course we're trying to get through each of these types in our notes. So the next thing that we're going to talk about is future value. We also have something called present value, which for some reason is not given on here. Okay. The present value formula is given on your formula sheet. And so it really just eliminates or kind of rearranges this 1 here onto a different side. But the idea between both of them, and they'll both use this versus PV, which will be your present value. For a future value, basically the idea is that you have something that you are going to be saving for. So basically you have $0 now, and in the future you are going to have lots of monies. Okay, versus present value, which means that basically you're getting a loan. You want money now. So as we look at it, you're basically saying I have lots of money all of a sudden now, and then in the future I will have none, because I will have spent it off to end up having whatever, that car, that house, but now I owe nothing on it. Alright, and so taking a look at this, you'll see that R here is going to be your regular monthly payment in dollars. Okay, that's usually monthly, but of course they can change it to yearly, but then you would just want to know that that regular payment is per year versus per month. So anytime the T or that time changes, it can kind of be inserted into each of these variables. So the next one here is N, which is the number of periods, or divided by, periods of payments, periods per payment. So in this case, we're going to take our k times our t, so that k was that, is it happening monthly, is it happening daily, whatever it happens to be, and then per time. And then I is your interest rate per period, which is actually r divided by k. So we're going to take the rate and divide it by the number of times that you have. So taking a look at our formula, again, instead of having an n, we're actually going to have a k times t. And instead of having an I, we're going to have an R over K. And that's actually how it's written on the formula sheet as well. So let's go ahead and apply this. So thinking about what we need here, sometimes they will say use the future value or the present value. And if they don't, then you do need to determine it. So apparently we have a really nice grandmother, and every month since we were born, she put $50 into a college savings account. So, day you were born, you had 0. Eventually, you will have lots of money. So, in that case, we are looking at our something to save for. So, we're looking at a future value. So, again, every month since we were born, we put in $50. So, that's actually going to be our R value. The savings account gets a 3.2%, so our rate is 0.032. And that's compounded monthly, so that means our K value is 12. And then our time is going to be 18, because she's going to stop when you are 18 years old and ready to go to college. So we want to know how much of that is going to be our future value. And again, that's because we have nothing now, potentially, and, well, the grandmother has nothing now and is saving. So, if we put that into our equation, alright, so here's our future value equation. So, again, we're trying to find future value, so we don't know that, but we can fill in our R as 50, that's how much she's putting away each day, sorry, each month. Then we have 1 plus our rate, which is 0.032, over our K, which we decided was 12. Then we're going to bring that to the K, which is 12, times the amount of time that grandmother is doing that, which is 18 years. And then that's going to be over the rate, 0.32 divided by the K, which is 12, and all of that before you multiply by 50. So, order of operations, super not exciting here. But the innermost part here is this fraction. So, 0.032 divided by 12. To that, still inside this parenthesis, we're going to add 1. Right outside the parenthesis, we're going to bring that to the 12 times 18. So, to the 12 times 18 is 1.7, lots of 7s. Then minus 1. And then to that, we'll divide by the fraction of 0.032 and over 12, which of course we could have multiplied by the reciprocal. And then to that, we're going to multiply by 50. So, turns out, after 18 years, your grandmother will have $1,478.97 for you. Isn't that nice? Yay! Okay, so this next one is again kind of the same thing. And this one's a little bit different because now they're trying to get you to find R given the future value. So we're going to kind of work backwards just a tiny bit. So, Ingrid is saving for a new car. So again, Ingrid has $0 and eventually she will have moolah dollars. So again, that's why it's future value. Also, I gave the formula to you. But either way. She wants to buy a new car in 5 years and wants to have $15,000 to spend. So that is the future value that she wants. Alright, so she can get a 4.9% interest rate, so yay for that. It's going to be 5 years. And we're talking about how often, so that's going to be each month. And we don't know what our monthly payment is. So we're going to take all of these pieces and put them into our equation. Remember that I is actually going to be, K, R over K. N is actually going to be K times T. And then again, this I is R over K. So we're going to plug in what we have here, and we have 15,000. That's going to equal our R, which we don't know, times 1 plus the R over K. So this is our rate versus our monthly payment. So 0.049 divided by K, which is how many times? So that's 12. That's going to be brought to the K times T, which is going to be 12 times 5. After that, we'll subtract a 1 and end up dividing by that same fraction as before of the rate over the number of times per year. So basically, this is a number. So we need to find that number that's being multiplied by R and divide it over. So how do we find this number? We need to do our fraction first. So 0.049 divided by 12. To that we'll add a 1. Then we'll bring that result to the 12 times 5, which is 60 as its exponent. Subtract a 1, and then end up dividing that entire result by the fraction of 0.049 divided by 12. Alright, so what you end up getting is 15000 equals R times 67.8328. So in order to solve, we'll divide by 67.8328. And so we end on our monthly payment that they need to set aside each month of, let's see, 15000 divided by our answer, $221.13. So their monthly payment to get $15,000 in 5 years is $221 per month. So if you find this account and you want to get $15,000, go ahead and put away $221.13 per month and you will get there. Sweet. Alright. Versus the previous problem, which of course got to about $15,000 but in 18 years. And so that's because of its rate at 3.2 versus this one was a rate of 4.9. Yikes. Okay. So we will have an assignment on this. And again, kind of the big takeaway here is your future value versus your present value. So which one do you use? You use the future value if you end up starting with 0 and getting to the dollar signs, versus you use present value if you end up having money now, meaning a loan usually, okay, and then end up in the future having nothing, but you know, you do have that item as well, so there you go. Kind of like the other one, you have the item now that you've paid it, but you have $0. Alright, so that is our interest exploration here.